Okay, hello everyone, and welcome to the lecture. Please confirm that you can see my screen and hear me clearly. Okay, thank you. Thank you. Just give me 1 minute. Okay, so last time we were talking about arithmetic instructions. We saw how you can do addition, subtraction, multiplication, division, right? And then we also started looking at the I/O ports of the ATmega328P microcontroller. So we just started the topic, and what we saw is that there are three ports, port B, C, and D on the Atmega 328P microcontroller. All of those ports are 8-bit, other than the port C, which is 7-bit. And again, it is 7-bit in the sense that 7 pins are available, but the internal registers which are responsible for configuring the port C, they are also 8-bit, but the output pin, the pins, physical pins available are 7 in numbers, right? So let's start from the same point where we left. This slide was basically about the basic pins, the important pins of the microcontroller, like where you need to connect the power, where you need to connect the clock generator, where you need to connect the ground, and which pin is the reset. And then we had looked like at port A, B, port B, and port C and port D. Again, remember this is at Mega 32 at Mega 32 processor. It is not 328P, which we are covering. That's why it has port A. Otherwise, at Mega 328P, which we are covering in the lab, it doesn't have port A. Okay. These pins are related to analog to digital converter, and we will cover these pins when we will cover the analog to digital conversion of the signals. Okay. Uh, just can you please give me like 2 minutes? That's Ramadan here and I'm fasting, so I need to break my fast. Just give me 2 minutes and I will be back. Okay, I'm back. We can continue from the same point. So, uh, actually, for programming any, as we have seen in the first slide, which I covered in the like previous lecture, to program any port, we have three registers. Like there will be three registers associated with the port B, pin B register, DDRB register, and port B register. Similarly, three registers associated with port C and three registers associated with port D. So we will later on see what is the function or job of each of these registers later on. But here is the idea. So for example, the like graphical depiction of the same idea which I said. So for example, for port A, again remember this is not at Mega 328P microcontroller, but the basic idea is same. So for port A, you have three registers: DDRA, port A, and pin A registers, which are used to configure and to communicate with the port A. Similarly, for port B, which is shown here, right? It has 8 pins. So you have three registers again: DDRB register, port B register, and pin B register. Uh, let me discard these drawings. So the uh, and all of these registers are 8 bits, right? And you have 8 pins on the 8 physical pins on the out on the on the pin layout of the microcontroller. But these registers, they are internal. Definitely they are internal to the microcontroller, right? And even in port C, which in case of at Mega 328P is 7-bit, it has 7 pins. So the thing is like, let me just change the color. So how things change for the pin port C, that you have only these 7 pins, uh, physical pins, but internal registers for the port C, they are still 8-bit. Okay. So what is the job of DDR register? So DDR basically stands for data direction register. And the thing is that each port, or to be more correct, each pin of each port can be used in two modes, in input mode or in output mode. Input mode mean that you want to read data from some external device or from some external sensor into the internal register of the microcontroller. And output mode mean where you want to send the data from the internal register of the microcontroller to the output, you want to place that data on the pin, right? And you want to send it to the external world, right? So you can use each pin of each port in two modes, input mode or output mode. And data direction register is one which basically defines or sets the mode in which you are going to use the pin of a port, right? So it determines the direction of the corresponding IO port. And DDRA, so for each port you have each port has its own data direction register, like direction register A, data direction register B, C, and D for ports A, B, C, and D, right? So remember that there are each of these registers, data direction registers, these are 8 bits, and we have also 8 physical pins, right? Other than for pin C, other than ports in case of ATmega 328P, right? So if you set bit nth bit of the register A of the data direction register for a port equal to 1, it means that you want to use the nth pin in the output mode. You want to use it as an output pin, right? But if you set the nth bit of the data direction register to equal to 0, it's mean that you want to use the nth pin of that port in input mode. Okay. Do you have any questions? Since it is like we are just getting introduced to the ports, and later on we will have the coding examples. So then when we reach that point, you can have some practice. Okay, so we talked about what is the job of the data direction register or DDR. Now we are going to talk about what is the job of uh, port register, and here basically X stands for it can be A, B, C, or D, and in context of ATmega 3828P it can be B, C, or D, right? And similarly pin X, here X stands for B, C, or D. So now we are going to look at what is the job of these register. So when your DDR register is equal to 0xFF, so what does it mean? It's mean that your port is configured as output port, because 0xFF means like you are writing 8 ones, right? You are writing 8 ones to the DDR register of any port, let's say port B, right? So you have configured, let's say, the port B in the output port. So in that case, your port X register, it will hold the data that will be delivered. If you in this port you will register in this port register, you will place the data that you want to deliver on the physical pins. You want to place on the output pins, right? Physically. So your program simply needs to write the data into this port. So first job is to write the value in DDRX so that you can configure the pins of the port in output mode, and then the data which you want to deliver on those output pins, you need to write that data in the port register, right? The same data, when you have configured your port in the output mode, right? In that case, the same data which you placed in port register, it will also be placed in pin register by default. You don't need to write in pin register. You just need to write in port register. The internal hardware will automatically also copy it into the pin register. So here is an like example, not example, but here the schematic of like how things work, right? So let's say you have the nth uh, bit of the port X register, right? So whatever you place in this bit of the port X register uh, through through a, what was this called? Through a transistor, it will become available on the output. So for example, if you place one here, so it will also become available here, right? And yeah, sorry, it is not called transistor, it is called buffer. So and what is this here, the nth bit of the DDR register, it will work as a control signal of the buffer. So if it is like if it is 1, then whatever is the input will become available on the output. And if you note, the same thing is put back in the pin register, the nth bit of the pin register. But if it is 0, then whatever you have in port in the nth bit of the port register, it will not become available on the output, because then it will be disabled here. Okay, but you don't need to worry about this internal hardware. You just need to like remember, or you need to know that what is the job of the DDR data direction registers, and what is the job of the port register or the pin register, right? So when a port is configured as the output in the output mode, so the value you want to place on the output or make available on the output pins, you need to put that value in the port register, and the internal hardware will also copy the same exact value in also the pin register. Okay, now here is the second case when DDR register is set equal to all zeros, which means that you have configured a port as an input port, right? All the pins are configured in the input mode, right? So in that case, so if it is configured in the input mode, it's mean you want to read the data from the external world, right? The data that you want to read the data that is available on the pins into the register, into the microcontroller. So the data that will be read from the pins, it will be placed in the pin register of that port. That is the pin register that is associated with the port, right? And in the case where you have configured a port as input port, in that case, the job of the port register, it changes, right? Its interpretation of how it is used is how this the way this port register used is changed. So in the case where you are using a port in input mode, then you use the port register to enable or disable the internal pull-up registers on physical pins of the corresponding IO ports. I will explain. So when you write 1 to the port register, it's mean that you want to enable the internal pull-up registers. And when you write 0, it's mean you want to disable the internal pull-up registers. But again, remember, this functionality of port register works when you have configured the given port in input mode, right? Otherwise, if you have configured DDR as like output mode, then whatever value you place in port, it will be delivered on your physical pins as output on the physical pins, right? So this is how it works. So you have, like, for example, you have configured, let's say you have configured the nth pin of the port X as input pin, right? So whatever external value like logic 0 or logic 1 is placed on this pin, it will be read into the register, into the nth bit of the register, pin register, right? However, the nth bit of the value of the nth bit of the port X, it will determine whether this whether this switch connecting the pull-up resistor with the power supply, whether the switch will be closed or not. So if the value is 1, it's mean that the switch is closed, which means that pull-up resistor is active, or it is it is enabled. If it is 0, the switch is open, which means that this pull-up resistor is not working. Okay. Now you can ask the question that why you need these internal pull-up resistors on the IO pins, right? Just which this is exactly the same figure we have seen in the previous slide. So to answer that, uh, here is the situation. So when externally logic 0 is placed, like on, let's say, on the pin N of the port X, let's say you place logic 0. So the pin N of the the bit N will have value of 0 here, right? Bit N of the pin register will have a value of 0, whatever, because 0 is placed on the input, right? So when externally logic 1 is placed, then it's mean that 1 will be placed in the nth bit of the pin register, right? However, what will be read in the pin register when we don't place any value on the external logic, like let's say you have not connected, and you have not connected anything with this pin, which means you are not driving any signal, right? So what will be then read? So that is a problematic situation, because let's say if you don't have this this switch is not closed, it is open, which means that pull-up resistor is not enabled. So in that case, what will happen, that the input pin will be floating. that is, it will be connected to no input. You are externally, you have not connected it to anything, right? So let's say externally you also have a switch which is open, so which means this pin is not connected to any voltage, right? So then what will happen, that random noise will be read as logic 0 or 1, and they will be stored in your pins register. Why that random noise? Because in the environment you will have the electromagnetic signals, and they will drive the logic voltage to uh, unknown values. They will drive the input signals to unknown values, which will be randomly treated as logic 0 or logic 1, and we don't want to have that situation, right? So that's why what we do is that uh, if we enable this pull up resistor, right? So if we connect it here, so what happened, that input will not be floating any it will not be floating anymore, which mean, let me change the color, which mean that if you place a 0 here, right? So you will receive a 0 in the pin register, right? Because uh, when you connect this switch, so what happen, that a current will flow, and here there will be some voltage drop, right? Some voltage will drop across the resistor. And let's say if this, I am just making up some numbers, let's say if this was 5, here you get 2.5, right? But if externally you place the 0 voltage, right? So it will like override 2.5 and you will get 0 here, right? And if you externally place, let's say, logic 1, which is like, let's say 5 volt, right? So here you will get a signal, high voltage signal, like let's say equal to 5. So which is treated as 1. But if you don't place anything, this switch, if you open this switch and you don't place any input, so what will happen? Still, you will be getting a low voltage. Still, you will be getting a low voltage here, right? So it is, you will be getting a voltage here. Still, it will not be a random voltage. It will be the same voltage amount, which uh, uh, which you will get after, depending upon the value of this resistor, like how much voltage is dropped across this resistor. So you will get a fixed value, not a like random noise here, right? So which is equal to 0, logic 0. Okay. So input pin is not floating anymore, and you have a stable logic value of when no input is provided. Sorry, it will be treated as stable logic value of 1, not 0. It all depends upon how much voltage is dropped across this resistor. If the voltage is dropped, the voltage, let's say if you have power supply of 5 and voltage dropped is 1 volt, and here you get 4, and let's say that anything greater than, let's say 2.5 is treated as logic 1, then you will get 1 here. Any questions? Again, you don't need to like worry about like, because it is all internal to the microcontroller, but it is better to know what is the logic behind having the internal pull-up resistors in the microcontroller, right? So the state of your IO pins, those your IO pins can be in like 4 states, depending upon the value of your DDRX register and your port register, right? So if, let's say, let's first take care of the simple cases, right? So let's say we are using DDR, our value of DDR register is 1. If the value of DDR register is 1, then, and it's mean that your and you are placing 0 in the port register. So if DDR register value is 1, it's mean you are using the port as an output pin, right? So if the value of 0 is written in the port register, it's mean on the output you get a value of 0. If the value of 1 is written in the port X register, it's mean you get a value of 1, output 1 on that port, on that pin, right? Now let me change the color. Uh, Now, if DDR register, the value of the DDR register is, let's say, 0, it's mean you are using the port in input mode, right? And if it is in input mode, then there are two options. You can either enable the internal pull-up register or you can disable the internal pull-up register. Let's say if we enable the internal pull-up registers, right? So what will happen that whatever you input you have, if like you drive 0 on the input, you will read the input. If you drive 1, you will read logic value of 1. But if you connect it to nothing, the input pin, you connect externally to nothing, still you will get logic 1 by default, right? However, in the case where you have configured the port as input mode, but you have not enabled the internal pull-up resistors, then in the case where you have not connected the pin externally with any signal, then it will be high impedance. High impedance means that there will be random noise, so your signal will not be stable. So when you will connect it with the input, with the externally with an input, you will read that value. But when the external input is not connected to anything, you will be reading in the pin register random values due to noise, like 0 or 1. You cannot reliably, you can not trust those values. Any questions? Okay, so then if no question, let's start with our first example. Suppose that we want to write a program that sends 1 to all the pins of the port B. Okay. So here, uh, remember, if we want to program, if we want to program or if we want to write any data to the port, which registers we need to manipulate, data direction register and the port register when we want to use that port in the output mode, right? So. Uh, so we need to first set DDRB register to all ones. Why? Because we want to write all ones or send all ones to the port B, right? So sending all ones to the port B. So here we on this port, if let's say if you had connected 8 LEDs, so what do we want that though all those LEDs are switched on, right? So which mean that we want to use this port in the output mode. That's why we want to first put one in all ones in the DDRB register, right? And then so this will only configure the port B in the output mode. It will not actually send the data on the output mode. When will the data be on the output port? When the data will be sent on the output port? When you will write the data in the port B register. Okay. So how we can do that? You write an immediate value 0xFF, which is hexadecimal form of 8 ones, right? You load that value into the R20 register, right? And then you send R20 to the port B, right? Remember here we are using the out instruction. We have covered it briefly in one of the previous lectures. So here, what does this instruction do? It will send the content of the R20 register to the port B register, right? But if let's say if I don't have this last instruction in my program, and I simply my program simply has these two instructions, and if I run it, I will not see any output on the if and let's say if I have 8 LEDs connected with this port B, those LEDs will not be switched on. Why? Because I have not configured the port in the output direction or in the output mode. So I need to include this last statement or last instruction, right? Where I'm saying put all ones in the DDRB register, which means configure all the output pins, all the pins in the output mode. Okay, so if DDRB is not set 0x to XFF, the desired value will not appear on the physical pins. Okay. Any questions? No. Okay. If no questions, then let's do this example. And actually, I want you to do this on your notebooks. So you need to write a program which toggles an 8-bit pattern of port B forever with the time between on and off states. So what we want to do is this. So you have like let me go to the previous slide and discard these markings. Now, yeah. So what we want to do in the next example is the following. So that you want to first configure this port B in the output mode, right? And then you need to first send all ones on this port and then wait for some time and then send all zeros on this port. Okay. So you are supposed to do this uh, in a loop, right? And for waiting or for putting the delay, you can assume that you have a function, so you can simply call that function. Okay. And if you don't know how to call a function, actually you can simply use, let's say if the name of the function is delay, you can simply put the instruction call delay. Okay. So again, I'm repeating, what you need to do is that you need to configure the port B in output mode, then send a 1 to all the 8 pins, then wait for some time by calling the function delay, which let's say we are assuming it is provided to you, and then send all zeros to the port B, and then do this in a forever loop. Okay. Now go ahead and do the example and let me know when you are done. You have 2 minutes to complete this. I can take you to this previous slide so that you can get the hints about uh, which registers are to be written. So if you are struggling and you think you cannot do this, let me know. Otherwise, I'm assuming that you are working on the problem and I can give you a little bit more time, okay? But if you think that it's not, it's difficult for you, so let me know so that I don't waste the time and I go ahead and explain the solution. Okay, let me walk you through the code then, right? So remember that we need to we need to program which registers, port B register and DDRB register, right? So in port B register, what we want to do, we first want to write, okay, there is like, okay, I said you need to write all zeros and all ones, but here there is a different interpretation. Like instead of writing all zeros and ones, we are just writing alternative zeros and one, and then we will toggle them, right? So first you need to write on the output 0 1 0 1 0 1 0 1, right? And then after some delay, you need to flip the bits, output bits, right? So each zero is flipped to one and one is flipped to zero. And since we want to use the DDRB, we want to use the port B in the output mode. So in DDRB register, what we want to write all ones, right? So this is what we want to do. Now, how we will do it in the program? So for that, you first put the value of 0xFF, which is 1, which is what? Basically nothing but 8 ones, right? So 0xFF is hexadecimal form of 8 binary ones, right? So you are putting that value or loading that value in R16, and then you are using the out instruction. You are sending the writing the value of R16 in the DDRB register. Basically, what you did here, you are making the port, you are configuring the port B in the output mode, right? And after that, first you need load this value zero, this pattern 0101, which is equal to in hexadecimal form 0x55. So you are loading 0x55 in R16, right? Using the load immediate instruction, and then sending R16 to the port B, right? This thing using out instruction. And then you are calling the function which is already, we are assuming is available, called delay. And after that function is called and it inserts some time delay, or it waits for some given time period, and then after that the next instruction that will be executed is this one, load immediate. In this instruction we are loading the bit pattern 0xAA, which is basically the hexadecimal form of 101010. So flipped version of this one, right? So you are putting 0xAA in R16, and then you are sending R16 into port B. So you are basically doing this here. You are writing this bit pattern in the port B. And then you are again calling the delay. And then you are saying, okay, do it in an infinite loop or forever. So jump back or relative jump to L1. And then again, same thing will be done. Okay. Any questions? Okay. Okay, if no questions, then let me simply how to say modify this example for you and ask you to do it again. Okay, so how can I modify? Okay, okay. So go ahead and now try to do this example. Write two alternative 8-bit patterns of 0xF0 and 0x0F to port B forever with the time delay in between. And again, assume that you have the delay function which you can simply call in your program. Okay. Now go ahead and do this example. You have 2 minutes for this. Let me know when you are done with this code example. I'm waiting. Thank you for letting me know. I was scared like maybe something is wrong today with my teaching and students are not responding. So maybe you needed one more example before you were ready to solve the examples on your own. Okay. So yeah, I can simply modify this one for you, right? So I am deleting these figures to not confuse you, right? So in load immediate, here you can simply first put 0xf0, right? I am also deleting the command and oh sorry. So you can first put to configure the DDRB in R16. I think I can keep this one, right? And then in the loop, what you are doing is that you can first put 0xf0 and then you can send it to the port B. You can call the delay and then you can write 0x0f in R16 and send it to the port B and call the delay again, and that's it, right? Okay. Now let's go to the next example, next slide. So here we are going to actually connect a seven segment and seven segment display, a seven segment LED to the port C of the microcontroller, and then we want to display one on that seven segment. So before I show you or I ask you to write the program for it, let me explain that how seven segment works. So you have uh, if you see you have like uh, the seven segment unit shown on the right side and it actually has eight LEDs and they are numbered here, like this LED which is like kind of not highlighted, it is numbered as 0 or it is connected to the pin 0. So this unit actually has eight pins, right? So the pin 0 is connected with the LED which is not highlighted or which is not turned on or switched on, and it is numbered as 0. The pin 1 is connected with LED 1. The pin 2 is connected with LED 2. Pin 3 is connected with LED 3 and so on. LED 4, LED 5 and LED 6. And there is a dot if you see here, right? And this dot is connected with the, it is called LED 7. It is connected with the pin 7. So in total you have 8 LEDs and 8 pins, right? So whichever pin you want, whichever LED you want to switch on, so it's on, you need to write one on its send one to its corresponding pin, right? So for example, if you want to display one, so what you do is that you need to write one on the pin number one and the pin number two because they are connected with LED one and LED two, and you need to write zero on all other pins, right? So here you have connected it with the port C, right? And again, we are assuming that we are using ATmega 32832 microcontroller, right? Not 328P. So in 328P, the port C has only seven pins, but here we are assuming we are using 32, so it has eight pins, right? So you are connecting the eight pins of the microcontroller, eight pins of port C of the microcontroller with the eight pins of the seven segment display, right? A seven segment LED, right? So, which means that which ports you are supposed to, which register you are supposed to program or write, DDRC register and port C register, right? So, what value you are supposed to write in DDRC register? Can anybody tell me? You can write in the chat box. What value should be written in DDRC register? Yes, we now because we want to use all the eight pins of the port C in the output mode, so we need to write all ones in the port C in the DDRC register and all ones in hexaform as 0xFF, right? And what value should be written, should be sent on this on the output pins, which in other words, what value should be written in the port C register to display a 1? What value should be written? Uh, yeah, think again about it. Okay, let me explain. 6 and 7, right? So 0 bit is connected with the zeroth LED, right? So this is 0, 1, 2, and so on. But we want 0th bit to be switched off. So here we write 0. We want the LED 1 to be switched on. So 1. We want LED 2 bit switched on. So 1. And we want all other LEDs to be 0, to be not switched on. So we need to write 0 in all other bits of the register port C, right? So which is equal to, in hexadecimal form, equal to 0x06. Okay. So once you know what values are supposed to be written in the DDRC register and the port C register, then rest is straightforward. You just need to write your program. So first you are putting 0xFF in R20 register, and then you are sending R20 register to DDRC to configure the port C in the output mode. Remember, we are naming it as the port C, but then there is also an internal register which has the same name, port C. Okay. So the physical port is also named as port C, and there is an internal register which is also named as port C. Okay. So then you are putting the value of 0x06 in R20, and then you send that value of R20 to the port C register, right? And then you enter in an infinite loop. So once this is executed, you will see one is displayed on your 7-segment LED. Any questions? No? Okay, if not, then let's go to the next slide. Okay. And this time I want you to do this example. A 7-segment is connected to the port C, display 3 on the 7-segment. Go ahead and do this example. You have 2 minutes. Okay, thank you. Let's wait for 2, 3 more people to complete. Thank you. Good. One more person before I go ahead. Okay, thank you. So again, it will be similar code as we have read in the previous slide. So you first write all ones in the DDRC register. Why? Because you want to use the port in the output mode, and then you need to figure out what value to be written in the port C, and how you can figure out by looking at this seven segment, right? So what LEDs we want to switch on? LED 0, 1, 2, 3, and 6, right? So 0, 2, 3 they are switched on, and then the sixth one is also switched on. So we need to write this value in port C, right? So first we write 0xFF in R20 and send it to the DDRC register using the out instruction, right? So now we have configured our port in the output mode. Then we write 0x4F, which is basically the hexadecimal form of this bit pattern. We write it in R20 using a load immediate instruction, and then we send it R20 to the port C register using the out instruction, and then we enter an infinite loop. So once you execute the program until this point, you will see that 3 is displayed on your 7 segment. Okay, now in previous slides, we have seen examples where we programmed a port in the output mode. Now we are going to see example where we program the ports in input mode. So let's say that we want to configure port A, which is not available in ATmega 328P, but the idea is same, right? Let's say you need to configure the port A as input and receive the data and save it in memory at address 0x100. So you want to receive the data from port A and then save it in the memory at this given address, right? So what you need to do, which register you need to write for configuring the direction of the port? DDRA register, right? And what we need to do other than that, like we use the DDRA register for what? For configuring the direction of the port. So if we write all zeros in DDRA register, it means we are configuring the port in input direction. The other thing is that we want to enable the internal pull-up registers. How we will do that? By writing all ones in the port A register, right? And how will we read the input value? The value from the pins of the input values from the pins of the port A by reading the data from the pin register. Okay. So uh, this is just a directive. You need to put a comma here according to, like, if you write this program in the Arduino IDE, right? So we are simply using the dot equate directive to say that my temp we are equating the my temp to address 0x10, which is the address where we want to write the data in memory, right? Then we are putting all zeros in R16 using a load immediate instruction, and we are sending R16 to DDRA, which basically means that we are configuring the port A in the input mode. Then we are inserting a NOP instruction or no operation. So no operation is that it basically means that do nothing. So we are just want to waste one clock cycle. Why? Because it takes some time for the ports to be it actually it takes some time for the how to explain it, uh, because the input before you configured it in the input mode on the physical pins, there is some garbage. We want to get rid of that garbage or some random values, right? So that's why we need to insert one NOP instruction, or which basically mean that uh, put a delay of one clock cycle. And after that, what you are doing is that you are reading the value which is placed in the pin register. So you are reading that value from pin register into the R16, right? And then you are saying, okay, now using the in instruction, right? And then you are saying now store the value of the R16 register into the memory address 0x10 using STS, store in the static memory instruction. Okay. Is it clear to everyone? Okay. So If it is clear, then let me is there a question? So the knob is only for the input. Yes, you need to put knob only when you are configuring a port in the input mode. So here, let me go back again in the full slide mode. So here you are configuring the port A in the input mode. So after that, you are required to put a knob. But if you are configuring a port in the output mode, you don't need to put a knob after that. Okay, so now let's do this example again by making a slight change. So let's say now I want you to configure not port A but port B, okay, as input and receive the data and put it at the address 0xFF. FF, okay. So now do this example on your own and let me know when you are done. I know, I mean, this is not different from what we have seen, but I just want you to internalize what we have learned in the previous example. Okay, good. I'm waiting for like three, four more people to complete. Nice, Carlo. Okay, it is not, the solution will not be much different. You just need to change the name of the registers and the address, right? Otherwise, the idea is same. Okay. Now let's go to the next slide. So in this example, uh, what we are going to do is to write a code which gets the data present at the pins of the port C. So we are going to read the data from the port C and send it to the port B indefinitely after adding the value of 5 to it. So we basically want to read the data from port C, add 5 to it, and then send it to the port B, which means that port C is configured as input port and port B is configured as output port. Okay, so again, give it a try on your own, and after that we will we will have a look at the solution. Okay, so you have 2 minutes for it. Go ahead and try to do it on your own. Oh, okay. I think I can go ahead and I can explain the solution here. Uh, so, uh, okay, before I explain the solution, in the previous, for example, in this example, here we are using out, right? And we are saying out port C, comma R20, right? Or for example, out DDRC R20, right? But again, if you remember from the previous lectures, we said like you need to first either include the header file, which defines these name of these registers like DDRC and port C, or if you don't want to include the header file, you need to use the equate directive to to define their addresses. So uh, in that sense, these examples are not complete examples. Okay, so here in this example, we are basically using the equate directive to first set DDRB equal to the address of the IO address of the register DDRB, right, which is 0x04. And then similarly, we are equating port B to the address of the port B register, DDRC to its address, and so on, right? So we are basically equating the names of the registers to their address, like port B, DDRC, pin C, and so on. And you can get the address of these registers from one of the previous lecture slides, right? So then we are first writing all zeros in R16 through the load immediate instruction and sending it to DDRC. Why? Because we want to configure the port C in the input mode, right? Once we have done that, we are putting all ones in R16 and sending it to the port C register. Why we are doing so? Because we want to enable the internal pull-up resistors. Okay. So we have now configured port C in the input port. We have also enabled its internal pull-up resistors. Then we are remember still in R16 you have 0xFF, right? So now you are sending R16 to DDRB, which is for configuring the port B in the output mode, right? After that, we want to do what? We want to read the value from port C. How we read the value from port C? By reading its pin register, right? So we are saying in R16 pin C, which basically means read the value from the pin C register and put it in the R16, right? Then in the R17 register, we are loading immediate value of 5. And then we are adding R17 to R16. Why? Because we need to add the value of 5 to whatever we have read from port C, right? So after add, we have the result in R16 register, and then we are saying send it to the port B. So out port B, comma R16. Now R16 will be sent to the port B, and then we do it in infinite loop. Okay. Any questions? Okay. So here we want to write a program which continuously sends out to port C the alternating value of 0x55 and 0xAA. Okay. So let me let me go to, yeah, okay. Now go ahead and do this example. It is very similar like what we have done in the previous examples. You simply need to continuously send the uh, values of 0x55 and 0xAA in an alternating way to the port C. Okay. So go ahead and do it and let me know when you are done. Please let me know if you are facing difficulty or you are not able to do it. And also let me know if you are like still working on it. I'm assuming, so I can wait 1 more minute. Thank you. Thank you, Brock. I'm waiting for 1 more minute. Thank you. Thank you. Let's wait for other people. Good. Nice. Okay. Good, good. Okay. Now let me walk you through the solution. Good job, guys. Okay. So it's straightforward, right? So since we are using the port C in the output mode, so what you need to do is like, yeah, first we are using the equate to like set the name of registers equal to its address. Same for the port C. And then we are first writing all ones in R16 register and then sending it to the DDRC to configure the port C in the output mode, right? After that, we simply need to send the alternative values of 0x55 and 0xAA, right? So we are first putting 0x55 in R16 and using the out instruction, we are sending R16 to the port C, and then we are putting 0xAA in R16 and using out instruction, we are sending R16 again to the port C, and then we do it in, so we keep repeating it in infinite. Clear to everyone, right? If not, let me know. Okay, so we have some like 5 minutes and we don't have quiz, so let me take care of these instructions. So in the previous previous examples, what we were doing, for example, if we want, we were write, like for example here we were writing in DDRC register the value of R16, which is 0xF1 FF. So we are setting all the 8 pins of the port C in output mode, right? What if I don't want to set all the 8 pins of the of port C in the output mode? Let's say I want to use only, I want to set only pin 0 of the port C in output mode, and I don't want to affect the mode. I want to just retain whatever mode of other pins is, right? So for that, I can use the instructions, bit manipulation instructions like SBI, right? So it will set the bit in IO register. So you can set the value of only a single bit uh, in a given register. So what is the syntax? You first write the name of the operation SBI, set bit in IO register, then the name of the IO register, and the index of the bit which you want to set equal to 1. Okay. So whatever index you provide, the bit at that location will be set equal to 1. So here is an example. So for example, if you say SBI port D comma 0, so you are saying set the bit 0 of port D equal to 1, right? All other bits, they will remain unaffected. Similarly, for example, if you say set bit SBI DDRC comma 5, so you are saying set the bit number 5 of the DDRC register equal to 1, which basically means you are saying set the pin number 5 of the port C in the output mode, and the mode of all other pins will remain unaffected. Whatever it would, original mode was, it will be retained, or initial mode was, it will be retained. Okay. So this is like the template. So this is the opcode. Then 6 bits are used, 5 bits are used to specify your IO register. So it can be anything from 0 to 31, right? And then your uh, triple B, the 3 bits, they are used to specify your bit index which you want to set equal to 1. And when we say 0 to 31, so it's mean like 0 to 31 mean 32 IO registers, not 32 general purpose registers. Okay. So this instruction cannot be used with the general purpose register because remember it is for IO registers. So you cannot say SBI R1, let's say for example, or R7, comma 5. If you say that, if you write that instruction in your program, your assembler will compile, will complain. So a complementary instruction to SBI is CBI, which actually does the opposite of SBI. So it clears the bit in in the IO register at the given index. So the syntax is that first you write the name of the operation, then the name of the register and comma, and then the index of the bit which you want to clear to 0, right? So here are the examples. CBI port D comma 0. So it's mean you are saying set the clear the pin 0 bit 0 of the port B. So which mean write 0 in the bit 0 of port D. Similarly, if you are saying CBI DDRC comma 5, so you are saying write the value of 0 in the bit number 5 of the DDRC register, which will do what? Which is actually configuring the pin 5 of the port C in input mode. Okay. And the mode of all other bits will be retained, whatever it was, the original mode. Okay. And again, this is the template here. So opcode 6 bits to specify 5 bits to specify your IO register and 3 bits to specify the index of the bit. Okay. Uh, let's try to do an example and after that we can stop. So here we want to write a program which toggles the fourth bit of the port B continuously. Okay. So first we are using the equate directives to set the name of DDRB equal to its address, name of the name port B equal to the address of the register 0x04, and then we need to toggle. So first we will set equal to 1 and then clear equal to 1, right? So here we are first setting the pin number 4 of the port B in the output mode. So remember, what does this instruction says? This instruction says set the bit number 4 of DDRB register equal to 1, which means that the pin 4 of the port B is set as output pin, right? And then so we have configured the pin. Now we will set the value what we want to deliver as output on that pin, right? So first we'll deliver 1, then deliver 0, right? So first we are saying right, set the bit, which bit number 4 in port B register. So it will be set equal to 1. And then we are saying clear the bit number 4 in the port B register. So and then first we will have jumping back. So like in real world, when you write this program, maybe you will see that if let's say you connect an LED on the pin 4 of the port B, so you will not see that the LED is like switching on and off. Why? Because there is no delay between these two instructions. So the value is driven on the pin at a very high frequency. The frequency is so much high that human eye cannot detect that the LED is switched on and off. So what you need to do is that in between these two instructions, you need to put some delay. Like for example, let's say you put a delay of half a second, right? Then you will be able to see that the LED which you have connected at the pin 4, first it is switched on, and then after half a second it is switched off, and again switched on, again switched off. Okay. Any questions? No? Okay. If no questions, then that's all for today. You don't have a quiz. You will have a quiz on Thursday. So let me stop here and we will continue from the same point in the lecture. Okay. Have a nice day.